Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and this is Lecture 30. We're almost nearing the end. We have, I believe this is the second last week, and we have next week is our last week of classes. But we still have some material to cover. I can already anticipate the questions. Uh-oh. How are we doing on the connection? Okay, excellent. Because YouTube was just saying that I was having a little bit of issues, but it looks like it's, sir, quiz is changed for Thursday. Yes, that's correct. Yep, that was announced last week, I think on Thursday. And the assignment was posted over the weekend. Excellent. Yes, so don't worry. It's not, we don't have a quiz today. It was just because gives you a chance to work on it this week. Again, it was a holiday. Okay, excellent. And of course, I was still marking the tests. I was, it's, I try not to mark them when I'm really tired. So like when I do start to get tired, I stop. Again, it's just taking me a little longer. Some of them are really, like some of the answers that I got were good. Some of them, it's taking me a little longer to read through it to see what's, again, if it makes sense, or to kind of write out some explanation like what's kind of going awry. Is that also the last quiz now? I guess that's up to you. Do you guys want a last quiz for next week? Or not? So you can say so in the chat. But if not, I vote yes, no thanks. What I will still do, though, is I will post an assignment. No, I think a quiz in the last week would be good. Other people are saying no thanks. Okay, so I think that Thursday would be the last session. So I plan to probably use the entire 50 minutes so that I can do a review, just kind of go over all the stuff. So I think I will forego the quiz. I will post an assignment, and the assignment will be a list of suggested questions. And again, doing the assignments is probably a good thing because those questions would also be fair game on the final exam. Okay. So we'll say that Thursday is our last quiz this Thursday. So it's the 8th of April is the last quiz. And there will still be one more assignment. Okay. So what are we going to do today? We're going to talk about the definite integral and the fundamental theorem of calculus. So, what the heck are these things? Well, we've seen the word integral before, and what we had done before was we had say a function, say x squared plus x cubed, and if I differentiated that, that should be straightforward. What is it? You should put that in the chat. What should be the, if I differentiate that, what should that be? Two x plus 9x squared. Two x plus 3x squared. Okay, so now I got two answers that are different. Is there someone that's going to 2x plus, okay, perfect. Yes, the 2x plus 3x squared is the winner. That is the one. So if I differentiate that, I use my prime notation. I'm not sure why there's a 9 in the one answer, which is 2x plus 9x. Maybe it's a keystroke error. Typo, that's what I meant. Okay, so we can differentiate that and we get 2x plus 3x squared. And remember when we had the integration, that undoes the differentiation. So you can see that integration undoes the differentiation. Okay. And we had seen other things too before. That's okay. If we have other ideas of so that's kind of like a function. We had looked at rates of change. Again, yeah, when we take the derivative, it's looking at the rate of change. So if we think of it like in a kind of a physical sense, so if I said I had velocity and I differentiate that, what should I get? If I differentiate the velocity, I should get what? I'm just going to look over at the chat. Yes, acceleration. That's right. So acceleration, so the rate of change of the velocity is the acceleration. And if I integrated that, so if I integrate the acceleration, so if I go from acceleration I integrate, then I get the velocity. And we've seen that before. So you can think of that as kind of an algebraic or a kind of rate of change approach. So this is kind of or you can think of it as a physical approach. But what's good for us in terms of when we're thinking about stuff intuitively, or I'm usually thinking in terms of pictures. So you have to tell me something. I have a hard time understanding a kind of a purely abstract form, so I like to think of it with images. So for instance, what does it mean geometrically? So geometrically, the integral represents the area under the curve. And you're going to ask me, what does that mean? But wait, it's pretty much how it sounds. But I'll draw some pictures. So geometrically, the integral represents the area under the curve. And so what I can do then is I'll pick a really basic function, like as simple as I can go. So we have our y, and here's our x-axis, and the simplest thing I can think of, besides drawing just a flat line, I'm going to draw a diagonal line. So here's my diagonal, or my y equals x line. And I'm going to drop a perpendicular right here. So there's my perpendicular at 1. And the question then is what is the area? What is the area under y equals x from x equals 0 to x equals 1? Can anyone guess what the area under the curve is? If you're really stuck, just think of what the area is. What is that shape that I just drew? I got a half of y times x, half y it's really close. It's even more simple than that, because I just said what's the area. Someone wrote 1 times f at x. I think you're saying squared, maybe. Someone's writing 0.5x. You're overthinking it. It's so what we can think back to like elementary school, and again I'll just shade this in here. It's like find the area. So what is this shape? Well, yeah, it's a half. Exactly. It's a triangle that we just drew, right? So we're going from here to here, and for here, the area is a triangle, and it's a half times the base times height. So in this case, the base is from 0 to 1, so the length of my base is just 1. And the height is at here, so that's my point here, which is 1, 1. So the height here is 1. So there it is, which means that the area should be 1/2. Now, how would I express this? We had done this with an integral before, we had written something like the integral of x squared dx. And the only thing that will change from what we call this is the indefinite integral to the definite integral is by adding a and b, or in this case, zero to 1. So the way that I would say this in words, it's the integral of x squared, and then of course we have the dx, which is with respect to x, and we have from 0 to 1, from x equals 0 to x equals 1. And so you can just write, you know, if you want to show off to your date, you can be like, look, I can express the area under the curve for this diagonal, because we're trying to avoid saying the area of a triangle, right? So you can be like, oh, well, the integral of x, oops, not x squared, it should be x. I don't know why I was writing that. The integral of x dx is from 0 to 1 is equal to 1/2. Okay. Now, your date might not be that impressed after she sits down and she draws the picture and she sees, oh, it's a triangle. Okay. She goes, okay, I want you to do the next one. And she says, okay, well, you did the y equals x. I don't think that line ever worked. Maybe I am in a very, very small dating pool. At least math people are like that. Nothing gets us more excited about, like, just conversations in general is just problems. Just coming up with problems, trying to solve problems. Puzzles. It's definitely what drives us. Okay. So the next one would be like that. She would say, okay, I want this, x squared. Find the area under the curve. This one is a little bit harder because we don't really have kind of an elementary formula that we've done. Like, we can't really, x squared, it's a parabola, it's not a circle, so we can't really use the area of a circle. What can we do? So that would be the question. What is the area under y equals x squared from x equals 0 to x equals 1? So graphically, what that means is this. So all this stuff under here, I'll just kind of shade that in. So from 0 to 1, and here's my axes. What this area represents, this area is from 0 to 1 of x squared dx. Okay, so the way that we could do this is we could do an approximation. And the way that they first started doing this back in the 1800s, there was an old, well, not an old man, but a man. He's not old anymore, he's dead. Problems have something to do with the derivative. Am I right? Or would the date not be impressed by my math skills? I don't know. Now we've gone into the completely hypothetical. We need to define more parameters. As other people have pointed out, maybe, she's not in math, she's in a different subject. So what we would do is we would pull out a piece of paper, and what we can do is, and so this is how the man, a German mathematician, his name is Riemann, and when they were trying to, so we talked about it earlier that Isaac Newton and Leibniz had come up with the ideas and the foundations of calculus, the integration and differentiation. But it took a long time for mathematicians in general, to just kind of pour concrete into this foundation. And the idea of a limit needed some more rigorous definitions. And so there is a man named Riemann. Also, he's quite famous for his Riemann Hypothesis. There is a Clay Institute prize that was set in 2000, and it's called the Millennium Problems. And again, he has a hypothesis, and if you could prove it, you get $1 million. No one has solved that yet. There's a lot of ramifications. It's very interesting. But so that is his name. 1, 2, 3, 4. Let's say 1, 2, 3, 4, 5. And we'll say that goes up to 1. This goes up to 0. So what we can do here, I'll pull out a different pen. So I've broken this up into 1, 2, 3, 4, 5 rectangles. And so I would have 0.2 here, I would have 0.4 here, 0.6, 0.8, and I have 1. And so while I might not be able to calculate this right here exactly, we can first come up with an estimate. And we know what rectangles are. We know, well, I mean, I drew it, but I mean what the area of a rectangle is. So the area of a rectangle is the base times the height. So what I'm going to do is I'll make a little chart over on the side here. So we'll start at x. So here's my table over here. We'll do f at x. And then the area of the rectangle is equal to the base times the height. So in this case, the base on each of these is 0.2. And that'll be multiplied by the height, which is going to be f of x. Okay. So I'll start with my values here. So I have 0, 0.2, 0.4, 0.6, and 0.8. And the function then at 0 would be 0. If I square 0.2, that gives me 0.04. If I square 4, that gives me 16, or 0.16 here. Same thing if I square 6, it's 36, so 0.36. And 8, that's 0.64. And then I would multiply this by 0.2. So 0 times 0.2 is 0. 0.2 times 0.04, that's 1, 2. So 1, 2, 3. So 1, 2, 3. 4 times 16 is, isn't it 30? Oh, no. It's got to be 16 times 0.2, so that's 32. So 32, 1, 2, and then the 1, so 1, 2. There we go. 36 times 2 is 72. And 64 times 2 is 128. And then adding this up, well, make sure I can add this up correctly. So 0.08 plus, whoops, 0.008 plus 0.032 plus 0.072. Okay. I got 0.24. Now this is, you know, it's a, so if I sum those, so that's a sum. So my approximation from 0 to 1 of x squared dx is approximately equal to 0.24. So this is an approximation. And the reason for that is because we have some error. So in here I have some of the area that I didn't count. I have some in here, here's some in here, and then some in here. So let me just kind of, this area, so your date will go, but what about that? So this area was not counted. Okay, so that's not. So what can we do? Well, make those rectangles even smaller. So again, so I have something like that. So I have like, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I'll go up to here from 0 to 1, and here's my y equals x squared. So instead now, what I've done is I've got rectangles now that have a base. So I have a base of 0.1. So in here there's 5 rectangles. Over here there's 10. So in this case I would have x and I would have f of x. And in this case, every rectangle is the same, so I would say 0.1 times the height, which would be f of x. So if we didn't have the power of calculus, you know, this stuff is quite tedious. And hopefully what we can do is spot some sort of pattern, and what I'm doing, I'm just squaring these terms here. And if I multiply by 0.01, it just moves it by 1 decimal place. Okay, so if I add those all up, I get 0.285. So again, it's a little bit more, some of the area that I'm missing here. So again, still got a little bit of area here. It's a little bit smaller than what I had above, but you know, it's getting better. So again, there's my approximation. So again, my approximation from 0 to 1 of x squared dx is approximately equal to 0.285. So this is the idea. We said that I have my definite integral from, say, a to b of f of x. Dx is approximately equal to the sum of the area of rectangles. From x equals a to x equals b. So that's what I have. Now, this is the idea of the limit where we can introduce. So again, you know, calculus. Again, the big idea behind calculus is limits. So what we could do is, it would be great is, what if we had an infinite number of rectangles? I'll say that it's n. So what I would like is that n goes to infinity. Or equivalently, that we have these small changes here. So again, here is like my delta x. Here's my small change. Or again, I could put it up here. See, my area is equal to the change in x times the height, or same thing up here. If I let there be a lot of rectangles, so I start getting really, really small. You know, I start dividing them all up, lots and lots and lots and lots and lots. So as n goes to infinity, so as I have an infinite number of rectangles, it means that the rectangle is getting really thin. There's not enough room, right? So it's getting smaller and smaller. So the width is also going to go to 0. So So that's kind of the idea, is that we get an exact value if the number of rectangles goes to infinity. So instead of using this approximation, what I'm going to do is I'm going to write this as the integral from a to b of f of x dx is equal to, so I'm going to have some points x1, x2, so that's what I'm going to say. I'm going to say that I have the value of the function at x equals 1, x1, and then we multiply it by the width. So in this case here, here's the height, and there is the width of the rectangle. And then I would do it for x2 delta x plus x3 delta x dot dot dot, so on and so forth until I got to that last rectangle, the nth rectangle. Okay, so right here, this would be rectangle 1. Here would be rectangle 2, the area. Three, all the way to the nth rectangle. And then this is where the calculus comes in. So we have n number of rectangles, and we said we get the exact value as we let n go to infinity. So we'll take all of that, take all this, and we put a limit. So as the limit goes from n rectangles to infinite number of rectangles. Okay, and if you wanted to know how that is calculated exactly, that width is equal to the b minus a over n. And if you wanted to calculate x, which is the value xi, so it's for the ith value, that's equal to a plus I times the width. Okay, so going back to this, if I wanted to set that for my integral from 0 to 1 of x squared dx, and I'm going to use my formulas here, so I have my delta x, we'll set the b is 1, and the a is 0 over n, so that's just 1 over n, and the ith, or the xi of value is 0 plus I times delta x, and in that case there's the 0, so that doesn't matter. I have I times 1 over n, or just I over n. And so I'm going to substitute in my values. Now, you don't have to worry about doing this. I mean, I'm just trying to illustrate the idea of the integral. So if you see me doing some weird algebra, don't worry, because the idea is that I'm going to show you this. I am not going to shy away from showing you how something works. But hopefully you watching me having to write all this out will make it appreciate kind of the beauty of the next item that I'll show you. Is everyone okay so far with that? I haven't lost anyone. I'm just going to factor out this delta x here. And I can start to do some substitutions, some more substitutions. That should be the limit. And I have 1 over n times. So in this case, it would be f at 1 over n plus f at 2 over n plus dot 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 all the way up to f at n over n, or that's equal to 1. Okay, then the next thing I can do is, so it's the function 1 over n, so it's 1 over n and then it would be squared. So I get 1 over n, so this is squared, because that's my function. This would be 2 over n squared, and up to here would be n over n squared. So then just expanding this out. And the other thing I see is that I can factor out this n squared because I have it written over every one of them. So again, I have 1 over n, so that becomes 1 over n cubed. And what I'm left here is 1 squared plus 2 squared plus 3 squared all the way up to n squared. Okay, so this is where the algebra might be, you might not have seen this before, but this is a sum of squares. And there is a formula for that. And yeah, this is just something that we know. It's n times n plus 1 times 2n plus 1 all over 6. And there's lots of ways of proving that, but again, I'm just trying to show you we're just summing up a series of squares. So you don't have to memorize that. Don't worry. So what I have then is the limit of 1 over n cubed, and then I can replace all that with n times n plus 1 times 2n plus 1 all over 6. Okay, so we're almost done. What I need to do is just do a little bit of simplification of that. What I can notice though is I can do, I have this n here and I can divide that out so that I'm left with the limit as n goes to infinity of 1 over n squared times n plus 1 times 2n plus 1 all over 6. And in the numerator, I'll expand that out because now this is something that we can handle. We have a limit as n goes to infinity, and we know how to handle limits with infinity. So at this point, this is something that I would expect you to be able to handle. So we can expand out the top here. So I have n times 2n, so that's 2n squared. N times, so I have n times 1 plus 2n, so that gives me 3n. And I'm left with plus 1 up top. And I'm left over here 6n squared. So is everyone okay so far in the chat? I haven't lost anyone yet. Again, this is something that we can handle with our dividing the top and bottom by n squared, so that I'm left with, sorry, where did the 6 come from? Oh, unfortunately, it comes from the sum of the squares. That's just a formula. Is that okay? That's something I don't expect you to know. Okay. But we can divide through by, we can still handle this. We know how to handle something like that. Divide by n squared on the top, as well as in the bottom. So I'm left with 2 plus 3 over n plus 1 over n squared all over 6. So I have 1 over n here plus the limit as n goes to infinity of 1 over n squared. And again, remember, we had the limit as x goes to infinity of 1 over x to the r. That is equal to 0. So all over 6. So that means that this goes to 0, this goes to 0, and I'm left with 2 over 6, or that's equivalent to 1/3. So you can already see how much of an error that we had when we were looking at our approximation. So like with 5 rectangles, we had an error of, and we had a third, so we had 1/3 minus 0.24. So doing that, I have a third minus 0.24 gives me or that's approximately equal to 0.093. Repeating. And if I had 10 rectangles, we had an error of 1/3 minus 0.285. Uh, 29 over 600, or that's approximately equal to 0.04833. So we're getting, what we saw is that as we increased the number of rectangles from 5 to 10, we decreased the amount of error. So we went from 0.09 or 9, well, getting around 10% to about half of that. So we decreased the error by a half. Okay. So after doing all that, you know, it may have felt painful, but, you know, you're probably, is there a faster way? And of course there is. This leads us to what we call the fundamental theorem of calculus. So that is, maybe I'll write it with here in something important, the fundamental theorem. So the fundamental theorem of calculus so if I have a continuous function, f is continuous, on the interval AB, then from A to B of f of x dx, that's equal to big F of B minus big F of A, where f is the antiderivative of f. So you're going, what does that mean? That means that for the answer, we could have just gone with is 5. Told to evaluate from 0 to 1 of x squared dx. They told us to find the antiderivative. So the antiderivative in this case, so it would be capital F. So this is the integral of x squared dx. And we know how to, we've done that before previously for the indefinite integral. So what is the integral of x squared? Just in the chat, what is the integral of x squared? Perfect. Yes. 1/3 x cubed plus a constant. Now, when we're dealing with the definite integral, we don't really have to worry about the constant. So here, anyways, yes, plus c. So here it would be, according to the theorem of calculus, the fundamental theorem of calculus, we would calculate this at 1, and we would subtract this from 0. So, I mean, ultimately, if you really were concerned, you could see that you have this. You have 1/3, 1 cubed plus a constant, minus 1/3 times 0 squared, cubed, plus a constant. This is 0. And so I'm left with 1/3 plus c minus c. So those go away. And I'm left with 1/3. So the c's will always cancel each other out. So again, you don't have to write those out. And now that we have the fundamental theorem of calculus, we can do lots of examples and calculations. So the second one would be, okay. For instance, you could be asked to do something like this. So here's my y equals x cubed. And that's at 2, and here is at -1. So the question would be, what is the value of the shaded area? And so part of that would be, okay, I need to express this as an integral. So it's going from, it's the area under the curve, or in this case, as it dips below the x-axis, it ends up the area that's kind of bounded between it and the x-axis. So it's the integral of x cubed with respect to x. And we're going to go from -1 to 2. So over here, what I can do is the integral of x cubed dx is equal to 1/4 x to the 4th plus a constant. But over here, what I'll do is I'll do 1/4, and I start at 2 to the 4th minus 1/4 times -1 to the 4th. 2 to the 4th is 16 over 4. And I have -1 to the 4th, so that becomes positive, so I have 1/4. So I'm left with 15/4. So that's pretty quick. So let's do our list of indefinite integrals. that we've seen so far. So we've seen that just using a power rule, we had the integral of x to the n dx is equal to 1 over n plus 1 x to the n plus 1 plus c. And that's where the exponent n cannot equal minus 1. And we had done that. We'd shown, well, we'll do that next one. So if I actually have, n is equal to negative 1, so I have 1 over x dx. We had shown that that was equal to ln, or the natural logarithm plus c. We also know if we took the integral of e to the x, which is nice and easy, it itself is e to the x plus a constant. And the integral of b to the x dx is equal to b to the x over ln b plus c. Okay, so we have our list of indefinite integrals. Let's look at this one. Let's look at the integral from 0 to 1 of 1 over x dx. So this is equal to okay, in this case we know what it is. It's up here is ln. So we have ln 1 minus ln 0. But does anyone see an issue with this? Is there any issue with what I've done so far? Anyone? I'm just waiting for the chat to see if anyone... Is there anything wrong with what I've done? He says, what about ln minus 2 minus ln minus 1? Absolute. Okay, someone's writing absolute. Sure. If I put the absolute bars, then again, the absolute value of 1 is still 1, and the absolute value of 0 is still 0. So it ends with a minus ln. Well, it's not quite as simple as that. What I was thinking of is here, I have ln 1, that is equal to, what's ln 1 equal to? That's right. Ln 1 is equal to 0. And what about ln 0? don't know about that one. So if I pull out my calculator, and okay, so I have ln 1. That's correct. That's 0. Okay. And I do ln 0 now. It's undefined, right? The math error means that it's undefined. So this is undefined. Exactly. It's undefined. And the reason for that is, if I actually look at this function here, here's 1 over x. This is my function 1 over x. Remember that that domain, or the function here, 1 over x, is not defined at 0. And so the domain is from minus infinity to 0 and 0 to infinity, but it doesn't include 0. And notice that if I wanted to look at the area under the curve, you know, it's fine, say up to here, here's 1, and I start to shade it in, okay, but this is going off to infinity. So it means that this area is unbounded, so it's not defined. So we'll have to kind of put a box around this. This is not defined. Because why did I write this at the very beginning, which says f is continuous on a, b? That means that it has to be continuous on that interval, and 1 over x is not continuous on 0, 1. So it's not continuous, so you cannot apply the fundamental theorem of calculus. The fundamental theorem of calculus, FTC for short. Okay, so you're thinking, was that a trick question? No, because again, we're using a tool, and if the tool is not appropriate, we can't use it to come up with the answer. So again, it's not continuous on that interval. In fact, it's discontinuous at x equals 0. So we can't do that. However, you know, if we changed our question a little bit, you know, if you still had to do something like that. Here's question 4. You know, we could use a different limit of integration. So we could go from 1 to 3, 1 over x dx. And just to kind of do a quick drawing, you know, it would look something like that. From 1 to 3, 1 to 3. Something like that. So that's okay, we can do that. And that is ln of 3 minus the absolute of 1. And again, you know, the absolute values I can take off. We know that the ln of 1 is 0, so that is just equal to just ln of 3. And on a test, that's good enough, or on the exam, that's good enough. Just to give you kind of a feel for it, that's approximately 1.0986. But that's good enough. You just have to tell me ln 3. What other examples could we do? We could try this one up here. Let's try, say, integrating with e to the x. So, in this case, so everyone's okay with that? It was the fact on this integral isn't properly defined because the 1 over x isn't defined at x equals 0. That's all good. Just checking the chat. Everyone okay? I'm just waiting to see if there's anyone that has questions about that. No, yes, yes, no. Okay, so to integrate this, it's just e to the x. So in this case, it's we'll do e to the 3 minus e to the 2. All good, excellent, excellent. And that's it. If you wanted to, you could factor out the e squared so that you're left with, excellent, okay, good. And again, you don't need a calculator. This is good enough. But let's see, e squared times e minus 1 would give me something of approximately 12.696. Oops. Okay. Here's the next one. So suppose the number of new daily cases of COVID-19 in a city follows. The function will say f at x is equal to 1.09 to the x, where x is the number of days. So this is the, what we're getting at is some sort of like, there's an exponential function. It'll look something like that, 1.09 to the x. And those are the daily new cases. So like here's like at a particular day, we would get like this many cases. On the following day, it would be this many new cases. So we can estimate that. So we're asked to estimate the total number of cases the city. From day 1 to day 50. Now we're just asking to if we just had a couple of days, if I had just, from 1 to 5, I would have 0.09 to the x, and I would do 0. So like for instance here, this is how I would do it, like to do it accurately. So 1 would be 1.09, 2, 1.1881, 3, it's easy for a couple of days. And then you would sit there and you would add them up, and there's approximately 5 cases. So in total over 4 days. But we can integrate those instead. So the approximation with the integral. So again, that integral would be summing up all of those for us. We would go from 1 to 50, and it would be 1.09x dx. And we would go and we know our list. So we look up here. So there's the integral of bx dx is equal to bx over ln b. So same thing here. Our b here is the 1.09. So it's 1.09 x over ln 1.09. And this is a notation also you might see common is they'll put an evaluate bar, and we'll say evaluate from x1 to x50. So you could see that as 1.09 to the 50 of ln 1.09 minus 1.09 to the 1 over ln 1.09. And just to simplify this, to the 50 minus 1.09. And that's it. That's all that we can do without pulling out a calculator. So at that point, that would be fine. So this is approximate equal to therefore, from day 1 to 50, there are approximately 850 cases. In total. Cool. So yeah, basically what I've done here is I've done my from here to here, let's say from here 1 to 50, and I found the area under the curve. So if you're watching the news and you see a curve or some sort of plot where you're seeing the plot of the daily new cases, then to get the total number of cases up until that point, you have to sum up all those points. And basically that's the summation, or if you wanted to approximate it, you're using the integral. Now I think I've done this previously, but we can find more, so we can solve more complicated integrals. Using these properties. Okay, so I think I had done this before, I'm not sure, but we'll do it again. So we said that if we had the integral and I had a constant c, I'll just ask in the chat to see if we had done this previously, that I can just pull that c out in front. I had done that one before, or does that look familiar? And I'm just going to ask in the chat. I vaguely okay. Okay, good. So we've done that, but we also can have a version, again, if I just tack on those limits, a to b, and I have c. Same thing applies, I can move that c out in front. So again, same thing. Number 2, it's the sum of functions. So if I have the integral of f and g, that's the integral of the individual ones. So the integral of f plus the integral of g. And the same thing applies for the the definite integral. So here over on this side is the indefinite. And over on this right-hand side is the definite. Okay, so what does that mean is that I can pull out constants and that I can apply the integral if I have a sum. So let's do an example. So in this one it says find the integral from 0 to 5 of this polynomial 2x cubed minus 3x squared plus 7x plus 2 dx. here. This is the and if you're really bored, like or you can do this faster, again, if you're doing this ahead of me, the answer should be 267. Okay. So if I'm going to integrate that, same thing. I'm going to integrate this. So I can think of this as 2 and integrate from 2 to 5 x cubed dx minus 3, the integral from 2 to 5 x squared dx plus 7, the integral from 2 to 5 x dx plus 2 from 2 to 5 of dx so the integral of x cubed is 1/4 x to the 4th. We're going to evaluate that from 2 to 5. We also are going to move on to the next one. We have minus 3. The integral of x squared becomes 1/3 x cubed, and that's evaluated at 2 and 5 plus 7. I have x, so that becomes 1/2 x squared from 2 to 5. And lastly, I just have dx, so that's just, so you can think of that as being 1, so the integral of 1, so our constant, so we're going up a degree, so that should be x, and that goes from 2 to 5. So you'll have 1/4 times 5 to the 4th minus 1/4 times 2 to the 4th minus 3 times 1/3 5 to the 3rd minus 1/3 2 to the 3 plus 7. I have a half, so it's a 5 to the 5 squared minus a half, 2 to the 2 plus 2 5 minus 2. And then we just slowly start working through this. You know, it's just a little bit of arithmetic now. So I have 2, and then 5 to the 4th. That's something I really don't expect, but that's 625. 625 divided by 4 should give you, well, we'll just leave it as that. 625 over 4 plus the constant. No, we don't have to worry about the constant. No. And the reason for that is because those c's usually cancel out. The c's like here. Remember when we had done this previously? When we had done the indefinite integral, which was the big f at x, and I had 1/3. This is doing the integral of x squared. So then the integral of x squared is 1/3 x cubed plus c. and I had evaluated that at 1 and at 0. And what ends up happening is that the c and the plus c. Yes. So if it makes you feel better, you can do it. But after a while, you don't have to do it. Uh, 2 to the 4th, 16, of course, over 4 minus 3. 5 cubed is 125 over 3 minus 8 over 3 plus 7. 25 over 2 minus 4 over 2 plus 2 times 3. 625 minus 16, 609 over 4. So then we have 25 minus 4. 21 over 2 plus 2 times 3 is 6. Okay, what else can I do? I can get rid of this. That's prime, that's prime. No, that's part of that. 2. Seven times 20 is 140, so then the 7 times 21 should give me 147. So the 609 plus the 147 gives me 756 over 2. I have the minus 120 plus the 6, so that should give me minus 114. The 756. Did I do something wrong? 120. Did I do something? 125 minus 8. Yes. Thank you. Thank you, thank you, thank you. So the 117 plus the 6 gives me 11. Thank you for the catch. That's good. 756 divided by 2 gives me 378 minus 111. 7, 6, 2. Excellent, excellent. All right. Page 8. Let's do another one. So this one is like another example. This one is evaluate from 1 to 8. 1 over 3. Sorry, I'll read this in a second as I write it out. So it's the integral of 1 over the cube root of x squared from 1 to 8. Yeah, that's really nasty looking. So what I'm going to do is I'm going to write that as an exponent. So I have a negative, it's squared, and I have a cube root. So really what they're asking me to do is to integrate x to the minus 2/3 from 1 to 8. And what's going to be tricky is just making sure I'm doing this correctly. So my exponent, so I'll have x to the 2/3 plus 1. And over here, I will also have the minus 2/3 plus 1. And I'm going to be evaluating this from 1 to 8. Make sure you're checking my arithmetic, right? So over here, 2/3 plus 1, that's equal to 1/3. So over here, I have 1 over 1/3. And same thing over here. Minus 2/3 plus 1, that should be 1/3. From 1 to 8. And I have 1 over 1/3, or you can write that equivalently as 3x to the 1/3 from 1 to 8. And I can now substitute my values in. Oops. So I have 3 times 8 to the 1/3 minus 3 times 1 to the 1/3. So the cube root of 8 is 2. And the cube root of 1 is 1, so I'm left with that. Or you can see that as 6 minus 3, or that's equal to 3. So again, that's also a little trick. Well, not trick, I mean tip. Rewrite the function. So you can apply a rule you know. Okay. Lots of examples today. This one says find from 1 to 4 t squared plus the square root of t minus 2 all over t dt. So again, I recommend to do this, which is we can rewrite this so that's a little bit nicer. So I can divide the t into each of these terms. So I'm going to do t squared divided by t, so I'm just left with t plus, okay, now I have, it's a half minus 1. So that means that I'm left with minus 1/2. So on the second term here, I have 1 over root t minus 2 over t dt. And again, I can rewrite that as t to the minus 1/2 minus 2 over t and I can start to integrate this. So the integral of t is t squared. Okay, and I need to have the 1/2, so it's 1/2 t squared. The next one that I have is, this needs to go up by 1, so it's t. I have a minus 1/2 plus 1, so that becomes 1/2. And then over here, that's 1 over 1/2 minus, and then I have 2, and I have the 1 over t. So that means remember that the 1 over x, that's equal to ln x plus c. So that means that here it's minus 2 ln t, and then I'm going to evaluate this from 1 to 4. So then substituting in my values, I get 1/2 times 4 squared plus the 1 over 1/2, that's just 2. So that is 4 to the half minus 2 ln 4. And I need to subtract this evaluated at 1. So I have 1/2 times 1 squared plus 2, 1 to the 1/2 minus 2 ln 1. And I know that ln 1 is 0, so that means that this is 0. I can just kind of keep working through my arithmetic here. So I have 4 squared, that's 16. And then 16 over 2 is 8. 4 to the 1/2, that's, or you can think of that as square root of 4, that's 2. So 2 times 2 is 4. And then I'm left with 2 ln 4 minus 1/2 plus 2. So 8 plus 2 is 10. 10 plus 4 is 14. Make sure that I did that. Ln 1 is, yeah, it's still 0. Did I make any mistakes in there in terms of my arithmetic? Oh, I need to be very careful because I've made a mistake. Yes. There. So 4 minus 2 is 2, plus 8 gives me 10. And then I have the half, so that is 9.5 minus 2 ln 4. Excellent. And maybe what else can I do? Make sure that I do, oh, maybe I'll do a basic example like this one. This one would be like find from minus 6 to 7 of the integral 2 dx. Oops, mine. That is definitely not to scale. So what I expect it should be, here's 2, and I would expect 6 plus 7, that should be 13. 13 times 2 should be 26. So that's just kind of roughly. But if you wanted to do it using your integration, you would have 2x from minus 6 to 7. So 2 times 7 minus 2 times minus 6. So 2 times 7 is 14. Plus the 12 gives you 26. So I think that's all the time that we have for today's lecture. Thank you guys and ladies and gentlemen, thank you for tuning in for this 2-hour lecture on the definite integral and the fundamental theorem of calculus. We got to see that, sure, we could approximate the area using rectangles, that if we let those rectangles get, we have an infinite number of them, which means that the width gets infinitely small. We can actually, as that limit goes to infinity, we actually get the exact value of it. What's nice about that is that with the fundamental theorem of calculus, we don't have to do, approximations like this, or to do kind of long, tedious calculations where we have to use limits and special algebraic manipulations like using the sum of squared terms. We can actually come up with simple rules to apply to calculate the area under the curve. Excellent. Thank you all. If you have questions, feel free to send me an email. Make sure that you're working on the quiz. We have our quiz on Thursday. And we also have, if you need help with that, feel free to also, the Math Center is there to help you as well. And I will see you all on Thursday. Thank you very much.